Hi, my name is Rohan Madaan. Today's date is September 24th, 2025, and today in this video I'll be talking about the chiral molecule ibuprofen. So ibuprofen is one of the most commonly used medications worldwide, and it's an excellent example of how chirality in chemistry affects human health. The IUPAC name of ibuprofen is 2,4-isobutylphenyl propanic acid. Its common name, which you'll easily recognize, is simply just ibuprofen. Jumping into the structure of ibuprofen, we can identify the main functional groups. So first we have a carboxylic acid group on the left. This gives the molecule its acidic properties and allows it to interact with enzymes. Secondly, we have a phenyl ring, which is an aromatic benzene ring functioning as a substituent. And third, we have an isobutyl group, which is also known as a 2-methylpropyl group, and that's attached to the phenyl ring. Finally, we have a methyl substituent on the alpha carbon, which is next to the carboxylic acid group. The carboxylic acid and the propyl chain form the propanic acid backbone of the molecule. So these functional groups kind of come together to explain both the solubility and the biological activity of ibuprofen. Jumping into the chiral center and the stereocenter configuration. The chiral center is located at the alpha carbon, indicated by the little asterisks on the picture, which is directly next to the carboxylic acid group. This carbon is attached to 4 different substituents: a hydrogen, a methyl group, the aromatic ring with the isobutyl chain, and the carboxylic acid group. So according to the Kahn-Ingold pre-log priority rules, the carboxylic acid group has the highest priority. The benzene ring with the isobutyl substituent is second, the methyl group is third, and hydrogen, which has the lowest atomic number, is fourth. And so when we place hydrogen in the back, the sequence from 1, 2, 3 goes clockwise, which gives us an R configuration. Kind of going into the next slide a little bit, but ibuprofen exists both in R and S forms, but inside the human body, the R enantiomer is converted into the S enantiomer, which is the biologically active form. And I know I just touched on this a little bit, but there's 2 enantiomers, the I-ibuprofen and S-ibuprofen. They're mirror images of each other. And because there's only one stereocenter, there's no diastereomers. So it's possible to form constitutional isomers if atoms were rearranged differently, but then it wouldn't be ibuprofen anymore. And kind of jumping into some of the uses of ibuprofen, it's a pretty commonly heard of medicine, and so people are pretty familiar with it, but it's classified as an NSAID, or a non-steroidal anti-inflammatory drug. You can kind of tell from the name, it's used to reduce inflammation, reduce pain, reduce fever. So beyond just everyday pain relief, ibuprofen is also prescribed for conditions like arthritis, menstrual cramps, different injuries related to sports. And so it has a really wide variety of uses, and it makes it one of the most important and versatile medications we have today. And the chirality of it plays a major role in how it works, since the S enantiomer is the reason that it has its own therapeutic action. And so those are kind of the main uses of ibuprofen. Thank you.